In this section, we want to discuss the relation between the solution to the homogeneous system and to the non-homogeneous system. So consider first the homogeneous system. Ax is 0, and the non-homogeneous system. Ax is b, where b is some non-zero vector. A is the matrix of the coefficients, and x arrow is the vector of the unknowns. And there will be two important statements, two important properties. If we call x sub gh as the general solution to the homogeneous system, possibly containing some parameters, and if we consider the solution to the non-homogeneous system x sub n, then what happens if we add these two? What happens if we add a solution to the homogeneous system and a solution to the non-homogeneous system? Try guessing yourself. Stop me for a moment. Try yourself. Okay, thank you for switching me back on. This will be a solution to the non-homogeneous system. This is easy to show because if we substitute this vector to the non-homogeneous system, then on the left we have a times the vector. But a times sum of vectors is a times xgh plus a times xn. No bracket mode. But the solution to the homogeneous system gives 0 when multiplied by a. And the solution to the non-homogeneous system gives b. So 0 plus b is b. So we see that this vector solves the non-homogeneous system because a times the vector is equal to b. And this is true for any solution to the non-homogeneous system and any solution to the homogeneous system. Their sum does solve the non-homogeneous system. So this is one important property. And another important property is that in this way, if you take any particular solution to the non-homogeneous system, and if you add all the possible solutions to the homogeneous system, then as a result, you get all the possible solutions to the non-homogeneous system. We miss no other solution. We get everything. And this can be shown this way. If you have two particular solutions to this one, they may be different, but not too much. They may differ just by a solution to the homogeneous system. So if we consider x1 and x2, this does not mean the first component and the second component. This means just one solution and another solution. And if we subtract these two, they may differ. The difference may not be 0, but they cannot differ too much. They can differ just by a solution to the homogeneous system, nothing more. Well, and this is very easy to show, because if we multiply this difference by a, actually trying to put this vector into the homogeneous system, then this is a x1 plus a x2. But if this vector solves the non-homogeneous system, then when multiplied by the matrix A, we get the vector b. And similarly, if this vector solves the system as well, then when multiplied by a, we get again b. And b minus b is 0. And that's the left-hand side of the homogeneous system. So this difference may be non-zero, they may differ, but not too much. They differ just by the solution to this system. Do you remember seeing these relations already? Yeah, namely for linear differential equations, right? This is a very surprising and strong result. It is true for any linear equation. It may be linear, it may be algebraic, it may be differential, or even another case, if it is linear.